It's my pleasure to open this seminar. I am chairman today. I am Amir Bogatishvili from Prague, Academy of Science, Institute of Mathematics. And our speaker today will be Peter Hastö from Finland. He's now University Turku, and his talk is about anisotropic generalized Orlicz spaces and partial differential equations. Hastö is educated from Helsinki University, and now it is big expert about variable exponent space and generalized Orlicz spaces or some and partial differential equation. And okay, Peter, you can start now.
Okay, thank you. And also thank you for inviting me to give this talk. So you can see the title that Amiran just mentioned it. So there are kind of two parts, anisotropic spaces and partial differential equations. Oops. So there is the abstract, which was already in the announcement. So let's move right on. So two main parts, and then also this number one is kind of an introduction or motivation of sorts. So then after the motivation, I will actually first talk about this, well, it says elliptic equations. Actually, I think I formulated it as a minimization problem. And then in the final part, I will discuss this anisotropic spaces. And this is because of the order in which this topic evolved. And I have also included in each of this section some strange assumption A1 or VA1. So actually, I want to explain and emphasize this part as well. It's maybe not as easy to see that evolution just by looking at the individual papers. So somehow the starting point was explained in this book, which I mentioned, which I have here. But now these are some newer developments. So let's go to the first part, motivating the assumption. And here I will use this double phase space or functional, which has been studied in many papers recently. So here I have first the definition of phi function or Young function, generalized Young function. So phi has two arguments. One is in a domain in space, in Rn, for instance, or it can be a metric space as well. And here, at this stage, the second argument is just a positive real number. So the assumptions, we have this kind of measurability assumption, and then instead of convexity, I have sort of three parts. Well, first of all, we still have to have a non-decreasing function. And then here are some limit conditions, how it behaves at 0 and at infinity. This ensures that we have a non-trivial case. And then instead of convexity, I have this assumption that phi t divided by t is almost increasing. So you can see if phi is convex, then since phi at 0 is 0, then the convexity implies that this phi t over t is increasing. So this is a generalization of convexity. And this definition is from the book that I mentioned. So there we kind of fine-tuned these conditions, and we have this general most general case, which is indicated by W for weak, then if it is convex and left continuous, then we call it a convex phi function and use this subscript C. So here are some examples at the bottom. So of course we have like t to the power of p and exponential t, which are classical examples of Orlicz space. Then this one here actually allows for extended real valued phi. So then we can also take this kind of function, which is, well, first it's 0 and then it jumps to infinity. So it seems like a stupid function, but actually this one is the L infinity space. And then here is the variable exponent example, the double phase example. For why this convexity is not so convenient. So here I take two convex functions and the minimum, but we can easily see that the minimum of these functions is not convex. It's growing like this, and then one, there is kind of a kink. So this is not convex, but it still satisfies this condition here. And once we have this kind of function phi from the previous slide, then we define this modular and norm like this. So this is very well known from Orlicz space theory and also generalized Orlicz theory. So all of these are standard definitions. For instance, we can take this Luxembourg norm, which is defined like this. So, oops, the difference, only difference here is that this basic definition is more general. So with phi like that, we get a quasi-norm using this method. And here at the bottom, I have written what the space is. There's different phi functions from the previous slide generate. So here you see this infinity times chi 1 infinity function generates L infinity. And well, we have variable exponent space here. We have this double phase space, which is often denoted by H, this functional. And then with this minimum, I think we get something like that. That is maybe just the equivalence of norm, not exactly that norm. So this is just a standard, but now recently several people have been doing harmonic analysis and calculus of variations for this kind of growth, and then some additional assumptions are needed. And here I want to focus in this talk on this A1 condition. So this name is not very good. It's just A because this is assumption. The first assumption was A0, then A1, then it's also A2, which is not needed here. So not very forward thinking in the naming, but now we have used this in quite many places, so I continue with that. So the A1 condition says that we can compare the value of the function at different points x and y, but this cannot be done for all values of t, only for a certain range. And that may seem kind of trivial or not so important, but actually it turns out that this range condition is crucial in this theory. Here I have actually two assumptions, two versions, so A1 and A1S. So in A1S, we have this measure of how large t can be is by t to the power of s rather than phi. So here is my first motivation why this A1 condition is reasonable. So we can say in this kind of restricted situation where this phi is monotone in the variable x, then we can say that this maximal operator, Hardy-Littlewood maximal operator, is bounded in L phi on the unit interval if and only if phi satisfies A1. So A1 is sufficient also in the more general case, but yeah, the only if we have to consider this more restricted case. Also some additional assumptions that I do not want to delve too much into in this talk. So I want to focus on A1, as I mentioned. Okay, so this was done in 2015 and also some years earlier. Mitsuta and Shimomura and other colleagues from Japan had a similar result, but they did not use the condition A1. I think their condition is actually like A11. So here instead of t to the power s, they have just t. So that is a more restrictive result. And of course, then you cannot get if and only if, as this next calculation shows. So I wanted to motivate this with this double phase functional, which is written here at the top again. So here we have this t to the power of p. P is the smaller exponent. And then we have a second part, which has t to the power of q. But this one has a coefficient a. And here it is worth noting that a is a function which is non-negative, but it can take the value 0. So this is not like a weight, which is almost everywhere positive. This is to the closed interval, 0 to some L. So it's a bounded function as well. So now, if we consider this condition, we have to compare this function at 2 different points. So I take just a fraction like this and do some trivial manipulation. So we get 1 plus something times t to the power of q. And then here, since it turns out that we cannot use any information from this ay, so I just estimate this from below by t to the power of p, and then get this result. So now, in order to control this, we can assume that A is Hölder continuous. This is what is usually done. And then from the assumption, here we have this restriction on t. So from here, I can solve t with respect to this norm and put it there, and then use the Hölder continuity to get this part. And then I get this upper bound for the right-hand side. And now we are interested in when this is bounded. And here, this x minus y is a small distance. So that means that this total exponent here should be non-negative. So we get this inequality. And this inequality is sharp with respect to this alpha, although it is not entirely sharp. This Hölder continuity can be slightly more general condition that is explained in our book. But basically, we get the connection between alpha and PQ and S. So this A1S condition is equivalent. A1 is equivalent to this one, which is usually formulated so that this you divide by P, so Q divided by P is less than 1 plus alpha divided by N. And finally this A1N, which is kind of a special case, just gives this. So here the point is that if this S is not correct, then we will not get sharp results. And this was studied for this general Orlicz case in this paper, and also in a previous paper with Peter Hastö and Mi-Kyung Lee. Okay, so here let me continue about this double phase functional. So here I have listed 4 results from Baroni, Colonna, and also from Ji-Hoon-ok. So they proved various regularity results for minimizers with a combination of an assumption on the minimizer, like it's Sobolev or Lebesgue or Hölder regularity, and then these parameters. And here they can be compactly stated that this U in W1S is combined with the condition A1S. And this W1S can be kind of replaced by the corresponding target of the Sobolev embedding, so LS star or C 1 over 1 minus N over S. So you can see if you take this gamma equal to 1 minus N over S and use it here in 3, then you end up with S divided by N again. And of course, in this number 2, this L infinity is somewhat stricter. So the embedding from W1S, W1N is of course not into L infinity, but to a slightly larger space. And in fact, in a paper with Ji-Hoon-ok, we also showed that here this L infinity in certain situations actually can even be extended to, for instance, BMO. Okay, but so the main point of all of this is that this S, which I'll remind you, is related to what is the possible range of T that we can accept in our condition. So that is related to the a priori known information about the function that we are studying. So if we know more about the function, so have a stronger information, which is to say larger S, then we can consider a weaker condition on the phi function.
So this class is by S increasing, yes, when S is bigger, yes?
Yes,
Yes.
correct. So you can see it here because there's
one, yes.
One lower bound. So since T is larger than 1, then this is monotone.
It's better to find as possible small s, yes?
Well, I mean, small s is a stronger condition.
Yes, stronger condition, yes.
Yes. So, I mean, a result is better if you have larger s because then you have a better assumption. But yeah, I guess depend on what your point of view is. Okay, so that was part one. So motivating why the range in this A1 is critical. And let me move on to the second part. And here, as I mentioned, this actually is VA1. But first, some general overview of what this is about. So we can consider these minimization problems with some general energy F. And we can also consider this non-autonomous case where F can depend on X. And of course, this pretty much looks like this function in the norm. And here we have the non-standard growth case, which will be explained in some more detail in the next slide or in a few slides. So it means that this F does not grow like some power. And yeah, I guess we don't need that part. Oh, let's see. So here you will notice that this is the isotropic case. So the dependence on the norm here is just the absolute value of the gradient. So this is exactly the same kind of function as previously, where phi depends on x and t is a real number. So in our paper with Jihon Ok, or my paper with Jihon Ok in this European Maths Society journal this year, we proved this result. Again, I don't want to or discuss the details of these other assumptions. So the point is we have this energy, so phi, and provided these sort of auxiliary assumptions are satisfied, then we can say that this VA1 condition implies Hölder regularity for any alpha, and if this VA1 holds with sufficiently small omega, then we get C1 alpha, that is to say maximal regularity for this kind of problem. And this generalized, well, first of all, variable exponent case and the double phase case, which, as I mentioned, was studied by these three people, and also many other cases, variants of these. So what is this VA1 that we introduced for this? So let me here display this A1, which was previously written, and VA1 as well. Here, this phi plus BR means that you take the supremum over x in BR, and phi minus means you take the infimum over x in BR. So here this is the same, written slightly differently, but essentially the same condition as previously. And in this A1 condition, we just have some constant L. But now basically for the VA1, V actually stands for vanishing. This constant L should be small. Excuse me. So the constant L should be small if we take a small ball. So we can write it with this function omega, which depends on the radius of the ball. So L is 1 plus omega. And then when R goes to 0, omega goes to 0, so the constant goes to 1. And additionally, here, this should hold not only from 1, but from this smaller value. So this was our original formulation, but then when we continued to study this, we noticed that as different formulation is actually more convenient. So here you see the thing that was previously 1 or omega has become 0, and instead here I have added some, added the same thing that I just removed from here. So this is basically a different formulation where we don't need to worry about this lower bound. And yeah, this turned out to be more convenient. Also, another kind of quality of life improvement is to have here also a constant multiplying this, but I didn't write that here. So this new version of the condition and well, the proof of this theorem, I will not go through that in any detail. It was quite long, but one of the main challenges was to use this perturbation argument. So the argument itself is quite clear. So we study a minimizer or solution of this kind of problem, but then we compare it to a solution of a different problem where this other phi b, does not depend on x. So this is an autonomous approximating problem. But the question for us was, how should this phi b be chosen in order to have the appropriate approximating properties? And in our paper that I mentioned in we did this kind of choice. So for like a medium part, values of t, so between some bounds t1 and t2, we just take phi from the center of the ball. But then in the sort of edges, so near 0 and near infinity, we just take p growth. So this kind of splicing in the end worked out for this autonomous case, not autonomous, the isotropic case. But when we were thinking about that, we had some difficulty figuring out how to do the anisotropic or quasi-isotropic case. Because there we tried something similar, but it did not work. So let me skip that and go now to the quasi-isotropic case and briefly mention what we did there. So here, how is this different from what was previously written? Well, you can notice that there are no absolute value signs around this gradient. So here, f, as is mentioned here, is a function from omega times Rn to positive real values. So instead of t here, second variable is now z, which is in Rn. And one approach is using this kind of structure conditions approached by Giaquinta and Giusti. So f is bounded from below and from above and from below by this kind of p growth, well, f and its second derivative. And then in the x direction, we have some modulus of continuity. So some years later, Marcellini suggested this PQ growth case or non-standard growth case. So here the lower bound is still P, but the upper bound is some different exponent Q. And interestingly, it is possible to give several results in this case as well. A common theme, if we use this kind of assumptions, is that this Q divided by P has to be sufficiently small. So, well, exactly how small depends on the result. But we wanted to consider this problem without this kind of structure conditions, so without comparing f to some specific power function, like c to the power of p, c to the power of q. And this is our assumption. Here again, there are a bunch of technical stuff, so you can skip 1 and 2. And this number 3 is kind of the quasi-isotropy condition. So it says that up to a constant, this second derivative is the same in all directions. So here, as you see, psi and psi prime have the same absolute value. So we are comparing the second derivative over a sphere in Rn. And well, it doesn't have to be constant as previous in the anisotropic case, but it can only fluctuate a bounded amount. And that is why we call this quasi-isotropic. So it's not quite isotropic up to a constant. And here, some weeks ago, Rosario Mincione gave a talk here as well, and he was considering these ellipticity ratios, so I thought it would be good to include that. Although this is slightly different, but I don't want to go to a detailed comparison here, just to mention it. Okay, so in this quasi-isotropic case as well, the main point is to not have these absolute values, which for some reason are written here. So the point of this theorem is to have no absolute values, and we can still get the same results. And if we look at this VA1, then this is basically exactly the same as previously. So, well, phi is now called f. This, of course, makes no difference. Here, the parameter is psi, which is any vector in Rn. Otherwise, the condition is exactly the same. So this result can be found in this arXiv paper. And with Jihon Ok, we are also preparing a second paper, which has this, well, the bounded minimizer, the C gamma minimizer, and this S in this condition. Okay, so here again, this difficulties in constructing the approximating functional. You remember previously we took 3 parts. This time it was we used instead this kind of transition functions, which are sketched in this drawing. And well, I don't want to go into detail and mention the conditions, but we see again we have this P growth near 0 and near infinity. But yeah, we needed some quite different methods to get to the same place. And of course, this is reflected in the fact that this theorem is basically the same, the condition basically the same, a proof is very different. So now I want I think the final 10 minutes, if I'm correct on the time, I want to link to this fully anisotropic case. So here I give a new basic definition. So you see the in contrast to previous, here is not 0 infinity but Rm. So this phi depends now on a vector parameter in the second place. And well, for this last part, instead of weak phi functions, I used strong phi functions. The difference is in the third condition, where it is assumed that with respect to psi, this is continuous in this completion topology of the positive real line. So here I mentioned several people who have
what is meaning Xi go to 0? Because Xi now it's Rn, yes?
Yes.
This convergence is by norm or by H variable, or this game?
Yeah, I guess you could add here in the limit absolute value of Xi goes to 0 and absolute value of Xi goes to infinity.
Or maybe also Prism convergence, HO variable.
Yeah, well, I should mention that like there are various assumptions possible, and I think several of these papers, instead of this, they kind of assume that there is a lower bound and an upper bound by an n function. So then that takes care of this question as well from
Yes.
Aniron. But yeah, for this thing that I'm explaining here, like very few assumptions are needed because it's quite basic. Okay, so here I have this actual convexity condition that's mentioned previously. If we take minimum of convex functions, the result need not be convex. And this is even more stark when this phi depends on vector in Rm, not just the real value. So I have this almost convexity condition where here inside is added constant beta. So would be, I guess, something between 0 and 1. So a weaker version, of course, if beta is equal to 1, then this is just convexity. And here actually we can show that this almost convexity condition holds if and only if phi is comparable to its greatest convex minorant. And this is actually a kind of bad situation if phi is isotropic. Then if we take phi minus, so the minimum of some convex functions, then the result will always be comparable to this greatest convex minorant. But in the anisotropic case, this is not true. And here I want to compare again two conditions. So this A1 is the same as before in this formulation with the +1 now. And this A1 was the one also used in the regularity paper that I mentioned previously. And I want to compare it with this condition M that was used by these people. all their co-authors, so were also mentioned on the previous slide, and I have written it now to emphasize the difference. So instead of assuming that the phi minus in B is less than this critical bound, the assumption M is that the greatest convex minorant of this function satisfies the bound. And well, since this phi conv is minorant, so less than phi, so we see that this M is a stronger version of A1. By the way, here I have only done the main version. Of course, we can define the A1S and corresponding MS condition as well. And actually, as far as I know, more precisely, this previous studies used the MP or M1 condition, not the M condition, which is more general. So here, let me use again this double phase functional to show why it is important or why this MS or A1S is not so convenient. So here is double phase, but with variable exponents. So instead of t to the power of p, there is t to the power of px, and same with q. So now, if we write the condition, do the exactly same calculation as in the beginning of the talk, this A1 condition and indeed the M condition gives this. So this, of course, is a isotropic example. So A1 and M are the same. And here we compare Q and P for every value of X. But if we try to use a constant exponent, so A, P minus, then we have to always divide by that P minus from there. And then we end up with this condition. So instead of comparing Q and P at every point and seeing taking the maximum over all points, here we take separately the maximum over P and the minimum over maximum over Q and minimum over P. So this is well, unnatural, I think, and also weaker. So this is just motivation why I think this M is better than MP. And finally, here is this theorem. So it turns out that these A1 and M are equivalent. And then we can also get this Jensen type inequality. This inequality follows quite easily from this condition M. So the point is just that if we use this theorem, we go from A1 to M and then obtain this inequality. And one slide about the proof. Actually, I don't want to say very much about that. Basically, the idea is that we define the second function ns, which is kind of a cone, but it's not a cone from a sphere, not necessarily. Rather, it is from some potentially complicated set, Ks, just defined like that. And then to relate this phi minus the convex minorant and phi minus itself, we use this minimum of the original function and this ns. So basically the original function, which is somehow convex, kind of cut it along this surface and then take outside just this linearly growing piece. And then show that this is almost convex, and then use this this result, that it is comparable to its greatest convex minorant, and that gives this result. So yeah, I wanted to mention some words about the proof, because in fact you can see that this proof is kind of similar to this idea from this minimization paper. Yeah, we basically just can use a much simpler cutoff function here, because in this problem phi doesn't have to be differentiable, so we can just take a minimum of these two functions. Okay, so here on the last slide are the papers in more detail. So these are now not in alphabetical order, but rather in the order, kind of logical order. So first, this A1 was introduced. In the second paper, this A1S was introduced. Then the VA1 was introduced for this to study the maximal regularity. And then once we continued to develop that, we obtained this anisotropic version of it, although for the regularity we could only use it in the case of quasi-isotropic functionals. But the condition itself could be, or was actually already fully anisotropic. And so in this final paper from earlier this year, I was then able to use that condition in this generalized Orlicz space setting. Okay, so that was all I wanted to say about this. You can find the papers on this website. And if there are any questions, I will try my best to answer. Thank you.